All right, so I was just saying that what we're doing now to evaluate the types construction is we're running the chain. We're starting from the row calculus, and we are running the different containers. So with set, there's nothing exciting there. We just get back the namespace logic. But we will look at a model category where we have a model of linear logic, and then look at a model category where we have some version of Hilbert spaces, assuming we can find a locally finitely presentable one, and look at each of the logics that are so generated. And then as a part of that construction, or as part of that effort, I was looking again at Girard Quantal's. Girard Quantal's, you start with a monoid, you lift the monoid operation to the power set, which is easily done. And then you pick out a set, which is a dualizing element. So this is like the complement of a prime ideal, or some such thing. So as an example, you can take a word in the monoid that is missing one of the monoid generators, and then you close up under that, or you close that set, and then you take the complement of that, and that'll be dualizing. At least I think so. So there are a couple of different ways you can select a dualizer. I was looking at whether or not there's a canonical way. So for example, you consider each of the Girard Quantals you get by leaving out one of the generators, and then taking the co-product of that. But then I wasn't 100% sure that the co-product of quantals gives you back a quantal. So I was doing a little bit of research on that. But anyway, so looking for the smallest free structure that'll give you a Girard quantal, and whether or not one of those exists. So that's another interesting little rabbit hole to go down. I would recommend, if you're interested in linear logic, looking at the Girard quantals, because they're certainly a fascinating construction, and was one of the first semantics. These are called the phase semantics for linear logic. So it's one of the first semantics discovered for them. But anyway, the point is to look at something that is freely generated, and then move, and then so that gives you the basis for your for the container, and then run the construction we talked about last time, using that as the container, and then looking at the logic so generated. So that's kind of the exercise that is required to give to go down that particular path. Yeah, it's interesting. Set is so ubiquitous that it kind of, there are all kinds of tricks that happen when using set that we don't notice. So there's, we build it's innocuous, or so it seems, that we build sets out of everything, but there end up being all kinds of crazy weird loops when you do that, and obviously Bertrand Russell's examples were just some that showed the absurdity of that, but there are many more. So you really have to be careful about the use of sets, and when you're looking at freely generated models of linear logic, you realize that a lot of what we take for granted in sets is not just lying around if you're looking at freely generated models of other structures. So anyway, it really exposes, how much set theory infects our thinking, because we take it for granted as a kind of background or backdrop to all the mathematics that we do. But anyway, that's all I've got for today. Are there any questions about what I've said or other things?
Yeah, I was wondering, is there a sort of a minimal or version 01 implementation of behavioral types that we could do that's not that doesn't have much research, or is there no such thing?
Yeah, I've answered this question several times before, so you can just go to the GitHub and find it. So there's the RowCamel GitHub repo has a minimal implementation that doesn't have any research left.
So is that, I mean, like to actually make it available on the RChain platform, then do we need to just convert that into Scala, or what do we need to do?
Yep, that's right.
Okay.
Yeah. So as I've said, the namespace logic stuff just works, and it can be applied directly to Rowlang. What we're looking at is a much bigger scope, so it works for any model of computation and a wide range of containers. So that's the goal of the research program. But the namespace logic stuff is ready to rock and roll. Just need someone to take it from the toy implementations to a production implementation.
I see. Okay.
Mm-hmm.
I have a. Go ahead, Thomas.
Greg, last time you mentioned papers from John Power about V-enriched categories, and I couldn't find exactly that. Is this the paper with Highland?
No. It's not V-enriched categories. This is the V-enriched Yoneda. So
okay.
So the idea is you're gonna switch out the base of, so instead of doing Yoneda over set, you're gonna do Yoneda over a V-enriched category. So you want to end up, which is basically, so what you end up doing is you're just swapping out the monad, the base of the monad. So it's V-enriched Levier theories, to be perfectly technically accurate. So Bill Levier showed that there's this class of presentations of a theory that correspond to monads, right? And that was the one of the components I was using when I was just looking at distributed flaws, right? So you construct a theory and you get this correspondence between the theory that you've used to present your model of computation and a monad. So that's the connection there. But a monad is an endofunctor. So you have to ask, well, what category does this monad live on? And the monad lives on the category of sets. So that's where the monad lives. And so what you'd like to do is you'd like to ask, well, if I swap out set for some other category, can I get the same kind of correspondence? And so it turns out you can, as long as that category is locally finitely presentable. And that's what Power showed. Does that make sense? Just, you understand what I'm getting at?
Yeah. I mean, I cannot say like completely understand, but yeah, I understand your words. Yeah.
Okay.
And
yeah. I mean, just the pic. I geez, I'm not at my desk. I'm using my phone, but the paper is. I mean, if you just look for V enriched Levere theories, John Power, there's like several of them.
I see. I'm looking at one, enriched Levere theories.
That's the one.
But-
That's the one.
okay.
Yeah, exactly.
Okay. Cool.
Yeah. And so there's work that he did. I don't know, like maybe 2008, and then he updated it or in 2010. Yeah. But the only constraint is that V has to be locally finitely presentable. So as an interesting pair of example and counterexample, so vect, where you can have potentially infinite dimensional vector spaces, is locally finitely presentable, but finvect, where you cannot, where you restrict to finite dimensional vector spaces, is not locally finitely presentable. So that's a pair of counterintuitive counterexamples. Mon, the category of monoids, that's locally finitely presentable. So that gives you a little bit of clues as to what's going on. Typically, if it's presentable, if the theory itself is a Levere theory, then it's locally finitely presentable. So the reason to zero in on vect is because fields are well known to not be finitely presentable. And so since a vector space contains a field, right, you have a field over a field distributed over a group, that's what generates a vector space. Then you would expect in general for vect to not be locally finitely presentable, but it turns out that vect itself is, while finvect is not. So that's so that gives you at least a little bit of flavor as to what's going on there, and it's worth doing some investigation. I mean, I can't say that I've done enough that I've got the understanding in my bones, but I have a better understanding than when I first started out, because I looked at several examples.
I see.
I have a FPGA hardware question, if I could.
Sure, go ahead.
Good. So Dimworm is interested in FPGA card to accelerate the row calculus processing.
Yeah.
And apparently, as I understand it, he's going to use a programming language called Clash, which is based on Haskell, to create an interpreter.
Yeah, that's what
on
that's what Gabi and I did. Yeah.
Okay. Well, so I guess I'm trying to understand, this the FPGA. For some reason, I'm thinking that it. So this creating of the interpreter, he envisions it to be relatively easy and fast to do. So I guess I'm trying to. It's not. Well,
and the reason it's not is because there's a lot of stuff that you can get to compile on Clash initially, but then when you take the next step, which is to generate the Verilog or the VHDL or whatever you're using as your target hardware, that ends up being then you have a much more constrained language. So there are several kinds of Haskell types that Clash will allow you to use and compile with, but can't do any synthesis for. So as an example, innocuous recursive types that you would think there would be a synthesis algorithm for, there isn't. At least Clash doesn't provide it. So that's where things start to get interesting, is that you have to get cleverer about the restricted language that you can use Clash to synthesize for. And that's why it's not quite so easy to generate an interpreter.
Okay. So when you said that you and Avi have created an interpreter, was it an FPGA interpreter, or?
Yes, that was our goal. We targeted an FPGA, and so I first did a tuple space implementation, and that turned out to not be synthesizable. And then I flipped it around, and we got it to generate. Oh, I can't remember. I might have still had a bug, but I came up with a scheme that I believe is synthesizable. I have to go back and look at how far we got, but we got something kind of limping along. And that was like good enough for his science project.
Okay.
Yeah, but that's like hardly what you want to use as the basis for like a production project. Yeah.
Okay. Yeah, and I guess I'm struggling to get an understanding of this world at FPGA. I guess there's with an FPGA card, there's multiple components, and an interpreter is just one of the multiple components. Is that how I would think of an FPGA card?
The interpreter is going to be a program. So the FPGA, just think of it as like a something onto which you can compile Verilog or VHDL or one of your chosen hardware languages. So like the way hardware is designed today, and again, this is just like a layman's view. It's more sophisticated than this, but typically what one does is to write down the design of your circuit using one of these high level languages like VHDL or Verilog or something else.
Right.
And that then gives you enough that you can go from that language to silicon.
Right.
Okay, but instead of doing like manufacturing the silicon, the FPGA provides a substrate where you can assemble what the silicon would do directly on the field programmable gate arrays. That's what FPGA stands for. So instead of manufacturing the silicon, you're realizing it on the FPGA.
Right.
Okay, so that's what the FPGA card is doing, that for you. And if you want to know more, there's a guy, he used Clash to do a Lambda machine, and he wrote it all up as like a blog and a video. So that's a really good, like, whatever 30-minute tutorial.
Yeah, because I was thinking, in this creating of the circuits, essentially you're taking the logic of Erlang and taking that at a high level and creating, a circuit which gets used by the FPGA card. So this idea of an interpreter, I'm not sure what it's interpreting if the circuit still has to be designed. It was that that connection between what's being interpreted and where's that something coming from, if it's
what's being interpreted as expressions in Rolang.
Mhm.
So that's what's being interpreted. So the way you build an interpreter is, the simplest possible way, which is, the way we actually do it in production, is you have a tuple space. So you want to manifest some kind of implementation of the tuple space, and then the interpreter just converts the Rolang into either storage calls on the tuple space or continuation calls on the tuple space, and that's it. That's all the interpreter has to do. But building the tuple space using Clash turns out to be non-trivial, and the reason is because you need a data type which is not synthesizable, or at least I couldn't find a simple way to synthesize that data type. But maybe Dimworm is a lot cleverer than I am and can find a good way to synthesize the tuple space. There probably is one. I was just like, I was under deadline, and it was a side project for Gabi, and I was doing a lot of other things.
Sure.
But maybe, I'd love to talk to someone about what's the best way to do a tuple space using Clash.
Very good. Thank you.
Sure. Any other questions or comments?
May I ask, I was watching some lecture from Emily Ryle, I think.
Oh, yes.
In the Institute for Advanced Study, and she was talking about infinite categories.
Infinity categories.
Infinity categories, yeah.
Yeah.
And she was mentioning, she was comparing type theory, set theory, logic, and homotopy type theory. And she mentioned something like Kari Howard Voevodsky correspondence. And she was trying to make like syntactic theory of infinite categories. And
I saw that talk, by the way.
Oh, and I'm wondering, is she gonna have another talk in a few years and say Kari Howard Voevodsky Meredith correspondence in that sense?
Oh, well, you mean if we present this alternative type theory?
Yeah,
it's possible. It's one of the things that I've argued, is that this is a better competitor for a decent type theory, because it breaks things down into components that we understand, right? So Martin Lerf type theory, it starts from types, but it doesn't, like, why are they types? It doesn't tell you. It just sort of, you're asked to accept that these are what types ought to be, and what, so like the angle that I've been taking for a long time is that, well, no, that's not really the way we think about types. If you think about types from the perspective of Curry Howard and the perspective of realizability, then types have a very specific structure, and this is what leads you down the path of operational semantics in logical form. And so from that foundational perspective, I think that there is, there might be a dialogue to be had there, but it's going to take a while before I think people get what I'm talking about.
As I understood, she was saying that this syntactic theory is more approachable than I think she said axiomatic approach. But she was saying that she was looking this from a category theory perspective, and just like comparing to type theory, which she said she don't know like enough. Is it make sense that category theory will be something like set theory right now, as you mentioned that?
Well, I mean, I certainly believe that category theory does not hold any special place in foundations, with the following caveat. Category theory let us understand something about the generalization of set theory itself. It allowed us to think about things from a particular vantage point. So then the whole algebraic set theory became possible to conceptualize. So Steve Awodi's work, for example. And if I hadn't been exposed to category theory, I never would have been able to come up with this whole idea of red-black sets, right? That is a very, very powerful idea. But I could, like, if I'd just been exposed to set theory and I couldn't conceptualize set theory as a theory, you know, as just another theory that could be mucked around with in the same way that we muck around with data types, then I never would have been able to conceptualize that. So category theory, and then the other thing, and this is where I think category theory needs a fundamental rewrite. If you rewrote category theory where the unit of conceptualization is the monad, then I think you would have a much more powerful theory. But it's a little bit tricky because, you know, in order to express a monad, you sort of need to have a notion of an endofunctor. So, you know, how do you bootstrap from the monad? That would be the trick. I think that would be that's a conceptual hurdle you have to get over in order to describe category theory where the monad is the unit, the most basic building block. Right. So for the standard presentation of categories is, you know, you've got some morphisms. Well, I mean, if you're going to go the infinity category route, you've got, you know, 0 morphisms and 1 morphisms and 2 morphisms and blah, blah, blah. And those are your building blocks. And my argument is that no, you're right. The right building blocks is some kind of monad. And then I think you're gonna have a much more utilitarian category notion, a theoretical notion. Because monad gives you really a handle on a notion of composition that is of sufficient power and generality. But that's just my funny way of looking at the world, very idiosyncratic. But go ahead.
I just want to ask, my understanding is that the monad is like every adjunction of categories creates a monad or something like that.
No, that's called tripleability. So it's not always. I mean, well, how do I say that? Yes, it's every time you have an adjunction, you can get a monad, but it's not necessarily the case that if you have a monad, you can split it into an adjunction. So this is the Beck tripleability criterion. The monads used to be called triples, and so there's a condition that has to do with when you have triples lying around. So if you're interested in that, go look at the Beck tripleability thing.
I'll definitely look at that. Thanks.
Mm-hmm.
I was wondering in this direction. There is lots of research on category theory, and she was mentioning, totally things that I don't understand, and the different single spaces or other categories, and I was wondering when I was listening Eric Weinstein or Sabine Hosenfelder about string theory, and is it possible that something like that happens? That it's so much research is going into some direction that some cognitive bias is created, and people don't look on other stuff, like similar to what they are saying for string theory, that explains everything.
There's no question. There's no question about it, right? There's no question. But the thing is, with mathematics, there's no criterion for what rabbit holes are important and what rabbit holes are not important, right? The mathematical universe is, it's bigger than any notion of infinity that has ever been proposed.
Yeah,
right?
that was my also question. What is really the foundations of mathematics? What
there isn't a single foundation. That's not the way to think about it. Yeah, you have to think about, pick the foundations that are useful for what you're trying to do. And there are lots of criteria, right? So one criteria is that it makes it technically easy to do, but that might not make it easy to explain. So explainability is another, so for example, for a lot of people, it's very difficult still in this day and age to explain things in terms of category theory. And so, by the way, I put the link to the Beck monadicity theorem, also called the Beck tripleability theorem, in your.
Oh, thanks.
Yeah. So explaining things in terms of category theory is going to make it less approachable by certain communities, especially computer science communities. You'd be surprised. So. Then if you set theory. So for example, if you're trying to talk to the distributed computing crowd, they have almost no experience with category theory. So if you're trying to explain some consensus algorithm stuff in terms of category theory, and then you have a major hill to climb, because they don't have those tools in their tool belt.
I see. So when she is connecting this to type theory, she's exactly doing that. She's trying to say the same thing, different words. So it's more approachable. So different kinds of people.
That's correct. So in particular, yes. Homotopy type theory has been super, super hot, pun intended, yes, amongst a certain crowd. And so she can enlist that crowd if she can talk about infinity categories in homotopy type theory. Yeah, so I'm not a fan of category theory as a foundation, because it is so obvious that it's slanted towards functions, and functions are just one way of thinking about compute.
And do you see maybe some kind of fix for category theory to be different, not so functions oriented?
Well, I mean, you could try doing a category theory like gadget that is based on process calculi. So you could try that.
Because look, listening these kind of lectures is so difficult to follow, and it requires very big knowledge about the category theory.
Yeah, I don't perceive it that way, but I've been,
I see. I mean, for me,
yeah, but I mean, really, I mean, it's what is she calling on? She's calling on Martin Lerf type theory. So if you have ever, I mean, you should be able to sit down with a paper on Martin Lerf type theory and get the basics, and then infinity categories. Again, what you want to do is, I mean, the idea is very, very simple. You have zero cells, and they have no constraints on them. You have one cells, and they have to run between zero cells, right? So, a one cell goes from a zero cell to another zero cell. Potentially, it's another one. It might be the same one, but it's a source and a target. And then you have two cells, which go from a one cell to another one cell, and so on and so forth, right? So that in your mind, you could be thinking about um, um, n-dimensional polytopes. You can be thinking about like there are lots of different ways that you can think about that construction. I gave around Christmas time, I gave another way to think about it in terms of graphs, right? But that's basically that basic structure is what's going on, and then you have to have coherence, some kind of coherence, right? Because that you have these equations that you need to satisfy, so you have to have identities, right? So you got it. So for the zero cells, you always have to have a one cell, which was going to go from a given zero cell back to itself, right? And so you're going to need identities for two cells. You're going to need, likewise, you're going to need associativity, right? So if you go from, if you have a one cell that goes from, the zero cell A to the zero cell B, and you have another cell that goes one cell that goes from B to C, then it's got to be the case that and then another one, right, that goes from C to D. So if you go from A to B to C, so that's composing let's say one cell X with one cell Y, and then composing the result of that with one cell Z. That's got to be the same as if you go from B to C and C to D. So that's composing Y with Z, and composing X in front of that, right? So those things have to be the same. So you have associativity of composition, and you have to carry that through at all levels, right? So the two cell compositions have to be have to be associative, and the three cell compositions have to be associative, right? And there's some other, and you can imagine, so like you have conditions about, within a given layer, within a given, in cell, you have some conditions, and then you can also imagine that you have conditions across layers, right? So this is like the Godemont calculus, right? So if I compose a one cell and then a two cell, and what's that? Or if I compose a two cell and then a one cell, right? What and in general, what happens at the n plus one boundary in terms of composition? So that's like the Godemont calculus, and again, that's like intuitively you can draw some pictures for yourself and see what's going on. So it's not super hard, right? Intuitively, it's very, very straightforward. And what she's trying to do is to code up those intuitions in the flavor of Martin Lerf type theory that is called homotopy type theory. And you can basically just forget, like if the homotopy stuff doesn't help your brain, right? So the thing about it is Martin Lerf type theory was around before there was ever homotopy type theory. And Blavatsky comes along and he appropriates a Martin Lerf type theory into the homotopy setting, giving it a particular interpretation in terms of homotopy classes. So you could, if you didn't have a lot of experience with homotopy apparatus, then you could just forget that and just think about it entirely syntactically, in terms of, think about it as a flavor of Martin Lerf type theory. And as a computer scientist or a computer programmer or software engineer, you have some experience with types. So you kind of know, what type systems look like. So you just start with Martin Lerf type theory. You see how she's encoding infinity categories into Martin Lerf type theory, and away you go. That's really all that's going on. It doesn't have to be super complicated. If you wanted to go down that path, you could kind of, instead of using Martin Lerf types, you could use, just Haskell types, just like or Scala types, right? What would you have to write down in a Scala type system to write down a type that gave you infinity categories?
Okay, yeah, I will definitely try thinking like that. Yeah, this makes sense.
Cool.
Yeah, thanks.
Sure.
Why are we interested in infinity types?
Infinity categories?
Continuous.
I'm not particularly interested in infinity categories, but the one thing about infinity categories that is nice is that it's parsimonious. So instead of just having like even to get to something even vaguely interesting like a monad, you have to go up at least as far as natural transformations. So you have to go at least as far as 2 cells, right? So already we see that in category theory, the notion of morphism really ought to be generalized. And so it would be really nice if we had like one presentation that gave you n cells, right? It's like you don't think about you don't want to have any special cells, right? It's just like there's a notion of an n cell, and there's a notion of composition of n cells, and there's a notion of what has to be true when you compose n-1 cells and n cells, and when you compose n cells and n+1 cells, right? So all of that has to be worked out in a way that is coherent. And so if you did that, then you'd at least have a category theory that was, appropriately parsimonious, rather than having like at each step you've got to work out by hand what the rules will be at that level. Like the Godemont calculus should not be worked out at the level of 1 and 2 cells. It should be worked out at the level of n and n+1 cells. That's the more like elegant, I guess that's the word. What you're looking for is an elegant presentation of category theory. So, but the problem that arises with infinity categories is there's at least 6 well-known definitions, and nobody is able to say why one is better than another.
I guess that my concern is, ultraviolet catastrophe. I mean, if we're dealing with constructible types, we we don't want to have singularities. Well, monads are singularities in a sense. But
I don't think of them as singularities. I think of them as closures, right? A monad is like a light cone. Everything that's reachable from here.
I guess the continuous stuff scares me. I don't trust it.
Well, no, but
if I'm considering constructible systems.
Yeah, sure, but there's nothing necessarily about infinity categories that's continuous at all. No. When they do infinity categories, they're only looking at, n cells. They're not looking at like anything between n and n+1. So there's no continuum there. It's all discrete jumps.
Okay.
So yeah. So but you raise an interesting question, right? I mean, if there is an elegant presentation of infinity categories where it's where what should happen is that there's an elegant presentation of infinity category, and that replaces this old notion of category theory, right? So you're not stuck with just objects and morphisms for your category. You have this crystal clear in morphisms presentation, right? And then it's just like this one presentation, not like, okay, well, there's morphisms, and then there's functors, and there's natural transformations, and then there's modifications between natural, all of that stuff is like replaced with one simple presentation about n cells.
As long as there's one infinity, we're okay. If there's more than one,
right, but as soon as you've got that presentation, you can now ask yourself, well, what does it mean to have 2.5 morphisms? What does it mean to have pi morphisms instead of 3 morphisms? What does it mean to have e morphisms? And probably all of those notions are perfectly well founded. They're probably all easily concretizable if you get your notion of infinity categories right. Then you should be able to find a continuum gadget in there somewhere. And the way you do that is, of course, is you have the Conway construction as an example. So you lift the Conway construction to your infinity category construction. So you've got a splitting, right? And on you have everything. You've got everything that's approximating from the left and everything that's approximating from the right, and then that would give you continuous infinity categories. I mean, I'm laughing because it's absurd, but it may, that's the thing, is like, Ramanujan studied theta functions and nobody had any idea what they would be good for. And then, 50, 60 years later, people start using them in cryptography. So, to me, it feels really absurd, that much structure. But who knows? It may, in fact, have all kinds of crazy use that I'm not anticipating. So that's the thing about mathematics. You cannot anticipate whether or not it's going to have any use.
Well, the whole notion of transfinite numbers has a certain, I guess, elegance. I don't know what I would call it, although, it's not really necessary in understanding any algorithm.
I would be careful with that last statement. Yeah. So
I think there's definitely some proofs there, which I don't know if I can find.
Well, like here's an example that I thought would be well worth exploring. I never really did it, But so you know, there's Robinson's approach to analysis using the infinitesimals, right? So Robinson develops this whole model theory for infinitesimals, and then he shows that any theorem you can prove in that model can be reduced to a theorem that can be proved, you know, in a model that doesn't use the infinitesimals.
Right. Yes.
Right. Okay.
It must be what I was. That may be the proof I'm thinking of.
Yeah. Okay. So, but here's an interesting approach. Think about it like cut elimination. So when we make a proof in, say, against style sequent calculus using the cut rule, we can always transform it into a proof that doesn't use the cut rule. And that transformation is an analysis, is a reduction. It's like a reduction of a lambda term, right? And more generally, we have this, you know, like you can do, if you get your logics right, you can do the same thing where you've got a logic for the pi calculus, and you know, when you do your reduction, you're getting rid of the par, right? So that scheme is very general. So does that, can you take that analogy and carry it out for non-standard analysis, so that the reduction of the use of the infinitesimals is like beta reduction? It's like cut elimination. So then that points to a language for doing computable analysis. Do you see what I'm driving at? See, so you can write down these you have a programming language in which you can write down these analysis problems, and then the evaluation of those terms is steadily removing the use of the infinitesimals. And if you think about it, this is kind of like what engineers do when they're, you know, they've got the dx's, and then they do the integral, and the dx goes away, right? So the dx's are in fact the infinitesimals, and then you put in an integral somewhere, and you evaluate the integral according to some rules, and it removes the dx from the expression. So the infinitesimals are going away. So there's an argument that this was intuited culturally, but no one formalized it in the setting that I'm talking about.
Thank you. I guess we're running out of time here.
Yeah, indeed. Thank you so much. I appreciate all the questions. See many of you in Dev Stand Up in 1 minute. Ciao, ciao.
Thanks. Bye-bye.